Right. Segment routing and flex algorithm. We know segment routing for a couple of years. We learned segment routing in service provider, CCA track. We also had a training before for the operators. And again, we are here in segment routing. And along with that, we are going to see how flex algorithm and segment routing supports the service provider network, the data center network. There are limitations in our traditional MPLS kind of traffic engineering or MPLS routing, I can say. MPLS with BGP, you may have policy-based routing or tunnel with RSVP, but they all have some limitation. We are going to discuss on that, and then how segment routing solves those barriers, removes those barriers, the limitations. Right. So we are going to see right from the fundamentals of segment routing, and then the architecture of segment routing. We have two different architecture. One with the MPLS, without MPLS. IPv4 needs MPLS for encapsulation. SRv6 have got inbuilt encapsulation, inbuilt. So those differences. And then the control plane. The logic in finding the best path with the label. Sometimes not simply the best path, there may be a constraint based path. And then the flex algorithm itself, which is purely a policy based routing. Policy based routing, like what we see in SD-WAN. In SD-WAN, we have policy to match the policy while selecting the path. It matches with the policy and selects the path. It matches with the, it looks for the policy to go to the destination. What policy need to be applied? Now, to achieve the policy based path selection, to have a policy based path selection, things like color, bandwidth, delay, those things are there. So not always the low cost path. Sometimes the low cost path may have more delay. Flex algorithm provides the flexibility to have different logical topology, because you got different policy for different traffic. You need different logical topology now because you got different policy for different traffic. Voice needs different policy based the path. The FTP needs different policy. In short, what I want to say is application aware routing. That's what we also say in ACI, Cisco ACI. SD-WAN is also an application aware routing, and that is what do you see here. Flex algorithm. is BGP with more smartness. That's what we have in SD-WAN, BGP with more smartness. That vSmart in SD-WAN, what it does? Flex algorithm. vSmart, we simply call it as OMP, but basically it is the modified version of BGP and its attribute. Nowhere it is said, that's my assumption, my observation. Modified version of BGP is what we have in OMP. The Cisco's overlay management protocol in SD-WAN. So when you go through this section, flex algorithm section, you will feel like you are in an SD-WAN class. So now you got an idea what is flex algorithm. Color, constraint, that's what. Now the configuration and deployment we'll see as the next class. Juniper configuration we need to test before we have a demo. I want to test with the images that we have, the image that's suitable for this configuration. Then we will have the commands in the presentation. Right now I did not put any commands. That should not confuse you. So we will test, and then I'll prepare a presentation separately for configuration and deployment, and then we will have a demo. So evolution of MPLS. MPLS uses LDP for label distribution, RSVP for traffic engineering. It's good, but when you compare to SD-WAN, you will find that MPLS with RSVP or LDP, this is adding more complexity. For whom? Not only for the engineer, even for the developers who develop some automation. Complexity. We have IGP protocol to provide you the best route. On top of that, we have MPLS LDP. On top of that, we have RSVP. So this is not that good for those developers who want to automate this. For them it is too complex. Complexity is that layer after layer you are adding. Instead, if you have single protocol to determine the control plane, then it is easy for the developers to automate it. Yeah, the problem is too many protocols to achieve traffic engineering in MPLS. And states are maintained in every router. What does that mean? We have local label, outgoing label, and that is for every prefix. On every router, for every prefix, you have different labels, locally generated labels. So every router need to maintain that state label, incoming, local, outgoing. We have seen that in binding table. So MPLS LDP binding will have upstream label, local label, and downstream label. The state maintained in every router. Even the troubleshooting is complex. We need to focus on IGP, and then focus on BGP, and then focus on MPLS, and then focus on tunnel, and then we decide where the problem is. That's how it is the RSVPT, complex troubleshooting. And we need to create many tunnels. If you have more and more customer, or more and more constraint based, policy based flows, not every flow is having same policy, different policy, then you need to create different tunnels, put them in different tunnel, which is not scalable. More tunnel is not good. More tunnel, more sessions to be maintained, not good, not scalable. You remember normal that security VPN, we don't go with site to site VPN when we have multiple sites. We go with DM VPN. Single tunnel can be established with multiple remote sites. Multi-point VPN. We want a dynamic tunnel, multi-point tunnel that is scalable. Fixed tunnel is not scalable. MPLS RSVPT is fixed tunnels. The path is dynamic. The path selection is dynamic, runtime. I'm not denying that. But you need to create multiple tunnels because you got different constraint for different application. Different constraint for different application needs different tunnel configuration, which is a scalable issue. So segment routing is a solution for all the problems that we have in MPLS, RSVP, LDP based environment. This becomes a solution for those limitations that we saw in that environment. What is segment routing? Segment based routing is the head-end router, the source router, decides the path, not every single router in the path maintaining table and deciding the next hop. The source injects the list of instruction. The source router encapsulates, encodes the path information inside the packet and tells that, hey, you go through this router, you go through this link. Instead of going to every hop and saying, I want to go here, how may I go? How should I go? And that router says, oh, you go this way. And then go to that router and again ask, I want to go to this destination, how should I go? And that router says, oh, you want to go there? Fine, you take this exit. That's not the one which we see here. Here, the head-end router will decide the path, and head-end router will insert the list of instruction that is needed for the path to be used, and as it goes, it simply orders the router that I am going this way. This is my path. I am going this way, and the packet moves because it has got already the list of instruction how the path need to be, or via which router the packet need to go through. Instruction is already there. It need not to depend on every router in the path for some instruction, for some routing decisions. This head-end router has already got the path end to end, and it has already encoded it inside the packet itself. Whereas in traditional MPLS, it is the network that decides the path. Every hop will be queried for a path, and they only will decide the next gateway. Segment routing, if we don't have, then we would have not had the SD-WAN or ACI. You might have seen that in SD-WAN, traffic from site A is allowed to go to site B and not to site C, which means the head-end router in site A should decide, not any router in the middle. For that, you need segment routing. But the word segment routing we don't see in SD-WAN, but this is the same story, same approach. So benefits of segment routing is stateless core, meaning no router in the path need to maintain any stateful information for the traffic that passed through it. And the control plane is not many protocol, it is simple one protocol, the IGP only. The control protocol is not like IGP plus BGP plus LDP plus RSVP. No, not that many. Just only one protocol you need for routing, and it's the same protocol will be used for SR, segment routing. All the label distributions are taken care by the IGP itself. Just by extension of TLVs, this can be achieved. Only IGP is needed. Next is built-in traffic engineering. Built-in traffic engineering. What does that mean? In SR we have built-in traffic engineering, meaning you don't need RSVP. You have flux algorithm. You don't need RSVP because you have flux algorithm. Built-in traffic engineering. Next is fast reroute. To take the alternate path when the primary path get into trouble during the runtime. During the runtime, the path gets broken. Now to adapt to the change, to get converged, less than 50 millisecond only will be taken when you have segment routing, because segment routing has got the fast reroute, topology independent, loop free, alternate, which is fast reroute. Less than 50 millisecond is guaranteed here. So all these things are needed for an SD-WAN or SDN, software defined network. Single protocol, built-in traffic engineering, fast rerouting. These are all SDN friendly things. So this is a simplified and scalable feature. Segment routing is a simplified and scalable feature. Right. Segment routing fundamentals. As I said, the head-end router is the one who encodes the path information into the packet. The full path information is defined by the source router, the head-end router, not the routers in the core decides it. And this path instruction is encoded into the packet itself. As the packet is received by the core router, they only read the instruction, and instruction says this is how you have to go out. You have to allow me go out on this port, on this gig Ethernet. Router says, okay, please go. That's it. That's the role of the core router. Packet itself comes with the command, give me this. I want to go via this. And router simply does that. Instructions. Those instructions are given by the head-end router. Right? The packet carries the path, and every hop the routers in the path need to simply follow the instruction. Same like Google Map. You want to go somewhere, you open Google Map and set the destination and say avoid the path which has got more traffic. Those things are constant. So now what the head-end router does is, in your cellular network, it calculates. It finds the best path, the paths which don't have more traffic, and it reserves the path. It creates a logical topology for this path from your home to the destination that you want to go, and shows you this is the path highlighted with the dark blue. This is the path that suits your requirement. Now, with that instruction in our mind, I keep moving, pressing the pedals, the accelerator. I keep moving, just focusing on the blue line shown in the cell phone or in the Google Map. You don't go to every junction and ask for an address. Google Map has already calculated a best path for you and is showing you very clearly with a dark blue line. There is also another light blue line, faded line, which is of similar path, but the best one is dark blue, and you simply follow that blue line, keep driving or keep walking. Same way, the path information is there in the packet. The packet needs to simply go to the router, and those routers simply follow the instruction and forward the packet. What is a segment? Segment is nothing but the instruction to forward. So a lot of segment IDs are going to be encoded into the packet. As the routers receive those encoded instructions, they know how to forward, where to forward, which link to use to send the packet out, to which node to send, via which link need to send. So segment is nothing but the instruction to forward. And that instruction may be pointing towards the the gateway, the router, the node, or the prefix, the subnet itself, the link. So the instructions that we have embedded maybe the node SIG-ID, can be prefix SIG-ID, can also be adjacent SIG-ID, link adjacent SIG-ID. Detail is coming in coming slides. Adjacent SIG-ID, prefix SIG-ID, node SIG-ID. So those instructions are simply telling the router, go to this router, or this is the link that I need to take. Now segment IDs or segment identifier, SID, a unique identifier for segment. Just now we saw segment is nothing but a router, or it can be a link, or it can be a prefix. When you focus on prefix, then you can have equal cost multipathing. When you focus on node, then it is single path, single router, node SIG-ID. Go to this SIG-ID means go to that router. Instead, if I have prefix SIG-ID, I just want to go to that prefix, and this is the prefix SIG-ID. Okay, then the router will see what all possible path. If there is multiple equal cost path, it's going to use all those paths to go to the prefix SIG-ID. And you have a particular path to take and a custom path, then you may need that link to take. I want this link to be used for this traffic. That is custom path. That needs link SIG-ID, link instruction. So SIG-ID is nothing but an identifier for segment. That segment can be a router, can be a link, alright. So this SIG-ID is basically label, and the label reserved for this is from 16,000 to 23,999. That is the range of number that will be used to identify a node or a prefix. Node SIG-ID or prefix SIG-ID will be of that range. The label between 16,000 to 23,999, totally 8,000 labels. 8,000 labels you have to identify a link. Sorry, not a link. Link is different. That's adjacent SIG-ID. We'll talk about that later. But to identify a node, to identify a prefix, you've got up to 8,000 labels. 8,000 labels. Now, MPLS label, IPv6 address. What I said so far is MPLS label, reservation, all this stuff. SRv6 don't work like that. SRv6 uses IPv6 address itself as an instruction. Yeah. See, that we will not focus now. When we go to SRv6, we will focus on that. That's slightly different. The instruction itself will look like an IPv6 address. Okay, now these instructions, the SIG-IDs are encoded into the header. into the packet. And these identifiers are locally significant as well as globally significant. For example, adjacent SIG ID is locally significant. Adjacent SIG ID is for what? For pointing to a link. When we got multiple paths, multiple link to go to somewhere, and you want to choose one particular link, then you may use this locally significant adjacent SIG ID. The prefix SIG ID and the node SIG ID are global. They are unique and they are global, and they are distributed using IGP. Right, this MPLS and IPv6 encoding, the concept wise the way that they operate is same, but the encoding that they do is different. As I said, IPv6 will use IPv6 address itself as a ID, whereas MPLS label uses a reserved global block starting from 16,000 to 23,999. So it's different encoding but the same concept. This is a core technology. This is the core concept, the very important slide of segment routing, according to me. Very important slide of segment routing. This is where people don't have clarity, especially those who come from Cisco background. Don't have a clear picture between node SIG ID, prefix SIG ID, why they are different, why they have given different name. Node SIG ID is to point to a router. Prefix SIG ID is to point to a prefix or a network itself. Adjacent SIG ID pointing towards a link. Binding SIG ID is pointing towards a list of SIG IDs. It may be node SIG ID or a prefix SIG ID or adjacent SIG ID or a combination of all these three in a bundle. What is that bundle for? The bundle is for the policy-based path selection. So binding SIG ID is something which many may not be confident. The reason is they might have not seen good example. We have a nice example coming, but I am going to explain it once again. Binding SIG ID is policy. What is policy here? I want the traffic to go through router 2 and then take right to router 7 and then take left router 9 and then go to the destination. See, I have a particular path. I have particular hops to be used. So we put all those instructions in one bundle and we point towards that bundle instead of pointing towards every SIG IDs. Don't worry, it's coming very clearly in this following slides. We'll see what is binding SIG ID with a nice example. First, the node SIG ID represents the router's loopback address. Node SIG ID is configured on loopback interface and it represents the router's loopback. See, it's a logical address. Loopback interface addresses are always used as the router ID, right? Here also same thing. To identify the node, we have loopback interface, router SIG ID. And this is used to find the shortest path. And this node SIG ID is advertised using IGP. So every router will have a unique SIG ID to identify all other routers. It's globally known. For default forwarding behavior, meaning you don't have any particular path option, you just want to leave it default, then you will see only node SIG ID being used. I'm sorry. Prefix SIG ID represents the network IP prefix. It's not the entire router, it is one particular network in the faraway router, in the distant, in the remote router. What is the advantage? We can have ECMP to go to that network, what are all the possible paths, and what are the labels for those paths. The prefix SIG ID is nothing but the IP prefix ID given to an IP prefix. That's prefix SIG ID. And it is useful for load balancing. As usual, this is also advertised using IGP. The previous one, the node SIG ID, is also advertised by IGP. Adjacent SIG ID. This is locally significant, meaning IGP will not advertise this to anyone. Only the directly connected router will know that this is my link and this is the ID for my link. This represents specific link interface. Why do we need that? So that we can force the traffic through specific link. That's what we want. We want some traffic to go by a particular path. So we simply use the adjacent SIG ID to force the packet through the path. Okay, this is something confusing for many, so I made it more detailed. Slide. Binding SIG ID. So this binding SIG ID, for example, you see down there, instead of saying go to router and then go to router 5 and then go to router 8, we use binding SIG ID 5000. What does that 5000 contain? It contains the list of instructions. So you mentioning the list one by one, you simply map to the list, because the list is identified using a ID called binding SIG ID, which is 5000 here. When you say 5000, it shows 3 SIDs, R2 SID, R5 SID, R8 SID. So we, instead of saying this SIDs in one after the other every time, we put them in we put them in a folder, and we call the folder 5000 means traffic should go to R2 from there, R5 from there, R8. let's read from the top, represents the SR policy. So this R, go to R2 and go to R5 and go to R8 is the SR policy. So binding SIG-ID is used for what? To abstract the complex path. Instead of carrying multiple SIG-IDs in the packet, you can use one binding SIG-ID, and the network will internally expand it into the full segment list. Yeah. So that full segment list we no need to give. We have a full segment list inside a folder configured on the head end router, and that is identified using a binding SIG-ID. So wherever you want to use that full segment list, you simply attach that binding SIG-ID. When packet arrives with binding SIG-ID, that becomes a big instruction list for the receiving router. Any question on binding SIG-ID?
No, what I'm getting is ideas with automate like with this the capabilities of each one.
Yeah,
Appreciate it.
This will definitely help automation also.
Yes.
Yeah, the binding SIG-IDs can be used in automation.
Perfect. Thank you.
Welcome. So the segment routing global block is from 16,000 to 23,999, and this is not for adjacent SIG-ID or binding SIG-ID. This is only for prefix and node SIG-ID. Node SIG-ID and prefix SIG-ID. What is segment list? Ordered list defines complete path. Right? From R1 go to R2, go to R3 and then to R5. So when the packet is received on R1, it inserts the list saying R3, R5. It puts the list which contains the SIG-ID of R3 and R5. Right, next, SR architecture, segment routing architecture. So, label versus IPv6. What does it mean? When we use IPv4, we depend on MPLS label. For that label, we use MPLS header. Whereas in IPv6, no MPLS header because you don't need label. Yeah. So currently we use labels. In future, when it is completely IPv6, we are not going to use that MPLS header. We won't have 3.0 as a 2.5 layer. There won't be a need. So IPv6 header itself is enough. No need of additional MPLS header. IPv6 header itself has got that extension for the instruction, the header extension, which carries all the instruction. And the instruction will not be like a label, it will be like an address, IPv6 address. It will look like an IPv6. Okay, so it has got native ID. There is no need for MPLS ID. It has got natively ID. So when you use IPv4 with SR, we use MPLS, and it's the same concept like what we have in normal MPLS. You have a push, you have swap, you have pop. Yeah, swap is also there. I was telling that this is not maintaining state in the core, but the core need to swap the label. For example, if the SIG ID, if the SID that I want to forward the packet is 5005, every router knows which router is 5005. When a packet comes with 5005, it will be swapped with the same 5005. Why? Because we are using MPLS header. That is how MPLS header gets encapsulated on every hop. Because we are using something which was there in IPv4 technology, which was there in a normal MPLS. This SR segment routing, though it is using IGP as a protocol for distributing the label, is the same MPLS header sitting there in the IP packet. As it enters into a router have to swap the label. That's how it is designed. But the difference is here it is swapping with the same label, not with the label locally generated. It swaps with the label that is globally used and advertised using IGP. So we do have push on the ingress, pop on the egress, and swap in the intermediate routers, core routers. This is same like what we used to have in MPLS infrastructure. There is no MPLS needed for segment routing version 6 because it has got the field called SRH, segment routing header. In the IPv6 header, we have this SRH. That's where the next hop or the instruction that is needed will be added, will be seen. Push, swap, pop, same like MPLS. Control plane. Control plane is IGP based. Only IGP. And it can be OSPF or ISIS. Popular with segment routing, ISIS is popular. ISIS SR. ISIS carries the instruction, it carries the node SID or prefix SID to all other router using the additional TLV, type length value, which is nothing but the field in the ISIS protocol header. So using the TLV, the SID is advertised to all other routers that runs ISIS and SR. Right. That ISIS SR is what preferred in the service provider network. Compared to ISIS, OSPF is less common. And there we saw TLV, here we saw LSA. Here the opaque field like type 9 LSA to type 11 LSA used in OSPF to carry the SIG IDs to other OSPF SR running routers. BGP in SR. Wherever you have policy distribution, inter-domain communication, we use always BGP, and now that BGP has got SR with it, so it can do better. BGP is between autonomous system. BGP is used in the place where there is a policy connecting different autonomous systems, inter-domains. Now, along with the SR, it can do multiple better thing. Example, SD-WAN, multiple sites, a big internet in the middle. We got different transport, MPLS, IP, LTE, etc. Now you can have various policies for that. BGP in SR is good. Any question, brother, so far? Segment routing in traffic engineering. You see, we don't depend on RSVP anymore because that is an additional layer for the developers, the additional burden, additional protocol. We don't need that. We can make use of the IGP protocol and the IGP protocol's database. That's enough. So to provide an explicit path, we just add instructions and give it to the router. Router follows the instruction and forwards the traffic. That's what called as traffic engineering. Not going with the defaults, giving custom explicit path info for the router to follow. SR policy. So we just now saw in the slide that we have an explicit path. That itself is a policy. I want my traffic to go this path. I got 10 different paths to reach that destination, but I want only this path. That's what traffic engineering is. That's what policy-based segment routing. Policy decides the path selection. Policy decides the path selection. And this policy is defined at the head-end router as an instruction inside the packet. In this SR policy, we use color, we use endpoint, we use segment list. This is a very familiar point for us. SD-WAN also uses the same term, color. For T-log, we use color there, similar. So the head-end router is the brain, and our policy is to tell the brain to compute a path and put the path information into the packet. And this all happens in the head-end router. Head-end router is the brain that computes and finds the path as per the policy, that matches the policy, suits the policy, and inserts it to the header. Head-end router, policy, and path. These are the components. Color is to identify the policy itself. Intent. Preference means prioritization.
Excuse me, color.
I'm sorry, brother? Your voice is breaking. Color is for intent, identifying different
Very good.
different paths.
Clear now.
Yeah. So preference is priority, we know. Endpoint is nothing but the destination. Okay, the path, three ways. One is the default, auto. For example, shortest path. That is dynamic path, which is also auto. We also have explicit path. We configure path. We provide the instruction, and based on that, the brain, the head-end router, directs the path, puts the instruction and sends the packet to choose the path. So candidate path can be default, and if that primary goes down, again dynamically it finds the alternate path. All those things are default. They are dynamic. They're auto, dynamic. They themselves compute it. The routers itself will compute and give you the best. You just give the policy to the brain, to the head end. The head end will decide the path. Whereas we also have explicit option where we tell manually this is the exact path it need to take. So three path options: explicit, dynamic, and auto. Dynamic and auto, they work together. Okay, we also have a controller. So you no need to dynamically or statically or manually write any path. You don't need to write any path manually. That's what I want to mean. Dynamic is seen in PCE, but what I'm trying to say is PCE is a controller. It's a software. It's a controller which will compute the optimal path for us. PC is a controller. Yes, it's a controller. It's a centralized controller. A controller which is seeing from a very high place, top view. From top, it looks at the ground. It looks at the network. So it will have better visibility. The PC application will have better visibility. So it can choose real optimal path. More about PCE is coming later. Now, topology independent loop free alternate is nothing but fast reroute. How? The head-end router not only have the best path instructions, it also have the instruction for the backup path, a pre-computed backup path, so that if something goes wrong during the runtime, Using the backup pre-computed instruction, the packet now will flow. So after the damage, it is not going to compute. It is pre-computed. So when damage occurs, it can use the pre-computed backup path, which will not take much time for the convergence, less than 50 milliseconds. Here comes the flex algorithm. As the word says flex, it's a flexible algorithm. It is flexible because it is going to understand our policy, bend according to our requirement. Flex algorithm, custom routing algorithm. Right, so you got a physical topology and you got logical topology. Using the flex algorithm, a logical topology is derived. And for that logical topology, instructions are added to the packet on the head-end router. That's the advantage of flex algorithm. Logical topology over the same network. Why flex algorithm? We know that OSPF or ISIS is going to take one shortest path. Comparing the metric cost, one shortest path. It's only one path. So all traffic should go through the same path, same topology, because of the metric. But the different application in our organization has got different expectation. Different application have got different expectation, which we call as SLA, service level agreement. For that, we need some paths with low latency for some application. For some application, I want high bandwidth path. For some, I want secure path, IPsec path. For some, I want it to go through a IPS device, service chaining. For these things to achieve, you need a flexible algorithm. Flex algorithm enables policy-based path computation. Do any question on what and why is flex algorithm? Thank you. See, for example, voice needs low latency and low jitter. Video needs high bandwidth. Financial application needs a particular deterministic path. No other path, only one particular path. Backup traffic, use the other available paths. This is my service level agreement. This is my expectation. This is the expectation of applications in my network. Not all application needs the same thing. They need different thing. This cannot be given by traditional routing. Traditional routing will only give the best path, which is calculated maybe based on the cost. But that may not have a low latency. That may have high bandwidth. The OSPF best path may have high bandwidth, but that may not have low latency, low jitter. Why? Every traffic is going through that one path. So how do you expect low latency and low jitter? That's why you need this flex algorithm in SD-WAN. Sorry, flex algorithm in SR. So this is exactly what the flex algorithm solves. Flex algorithm allows the network to compute different paths based on the constraint. So it uses different metric, not just one cost as a metric, delay, traffic, etc. So it includes or excludes the link using affinity, color. Affinity is nothing but the color. I like this path, meaning I have affinity to the path. So based on the color, it decides the path and the instruction to go through the path is decided. So Flux algorithm helps to achieve this. As a result, now the routing is not simply routing based on the best path, it is application aware routing. Because each application has got different demand. Each application have got different demand, different expectation. To identify the path that matches the expectation, Flux algorithm is needed. As we saw here, voice needs a low latency, low jitter. Video needs high bandwidth. For example, here we have three link. Link A, low latency but expensive. Link B, high bandwidth path. Link C, cheap but slower. See, these are all three different options we have in our network. Now, what this Flux algorithm can do? It can provide you link A for voice, because voice, or though it is an expensive link, voice are tiny packet, it won't consume much bandwidth. At the same time, low delay, so your voice can reach on time. Video is given high bandwidth link, backup is given the cheapest link. It's just a backup. Same network but the different path. Same network but different application takes different path. So the key value of Flux algorithm is to move to a network-centric routing. To move from the network-centric to the application-aware routing. I repeat, so far without segment routing we were doing just network-centric routing. Whatever the routing protocol says is the best. But this time it is the application. Application-aware routing.